When we train a modern large language model to align with human values, we typically lock its behavior onto a single, inescapable track. The mechanism causing this inflexibility is standard reinforcement learning from human feedback, or RLHF. It evaluates the model's outputs using one scalar value. During training, distinct human preferences, humorous versus helpful, are mathematically compressed. They get squeezed down into a single reward value, R. By optimizing for that number, the model commits to a fixed average behavior. This average approach fails in real-world applications, where context demands dynamic shifts. A user might need a model to execute a highly efficient, task-oriented query one moment, and then shift to a highly empathetic tone in a sensitive medical context the next. Building a truly personalized AI means throwing out the scalar reward entirely. Instead, we have to treat alignment as a problem of multi-objective optimization. The naive engineering solution to providing personalization is brute force, training a completely separate model for every specific combination of user preferences. Methods like multi-objective direct preference optimization or interpolating multiple model weights through rewarded soups demand massive compute. When you try to apply these strategies to models with 7 billion parameters or more, the training costs become devastating. A paper from researchers at Ruhr University Bochum and others presents a structural alternative, multi-objective control, or MOC. MOC trains exactly one LLM, but at inference time, that single model can dynamically navigate an infinite spectrum of preference trade-offs based on what the user requests. The researchers achieved this level of multi-objective control for the exact same computational cost as running standard single-objective RLHF. To see how they bypass the scaling bottleneck, we have to examine how MOC completely redefines the optimization target during the training phase. MOC sets a very specific control target. It forces the LLM's expected reward vector to directly match a continuous preference vector provided by the user. This fishwood plot shows an agent balancing wood and catching fish. The dashed ray indicates a user preference. Engineers often try linear scalarization, assigning percentage weights, but data reveals a failure. Outputs completely ignore the preference ray, violently collapsing to the extreme axes. This happens because linear combinations mathematically cannot locate solutions that sit inside non-convex or concave regions of a Pareto front. This collapsing phenomenon is a widely documented flaw in convex optimization when dealing with competing rewards. Soft mathematical weighting is clearly insufficient for true alignment. To control the LLM's trade-offs, the system requires a hard structural constraint. MOC abandons the practice of balancing multiple loss functions. It relies on a rigid optimization constraint applied directly in the reward space. MOC targets the mean squared error between the policy's expected reward vector and the user's numerical preference vector. To enforce this, the architecture applies a ReLU hinge penalty, defining a boundary threshold denoted as phi around the target. If simulated behavior deviates past the threshold, the reward incurs a massive mathematical penalty, forcing strict compliance. Returning to the fishwood scatter plot, we can see the geometric result of this constraint. The output data points now tightly hug the dashed preference rays across the entire curve. The hinge penalty accurately solves the geometry of alignment. However, integrating it directly into the policy gradient introduces a massive computational barrier. Calculating gradients for this multi-objective equation using standard methods requires memory that would instantly shatter the compute budget of any large language model. Standard solvers for multi-objective gradients use a min-norm calculation. This creates an n+1 backpropagation problem, requiring a distinct backward pass for every single objective simultaneously. Performing multiple simultaneous backward passes through a network containing billions of parameters is functionally impossible. The paper circumvents this hardware limit through a mathematical proof titled Theorem 1. Theorem 1 derives an upper bound surrogate objective. This mathematical substitution completely alters the optimization pathway. Crucially, inside this new formulation, the gradient of the policy parameter, nabla theta pi, is completely removed from the min-norm calculation. By dropping that massive parameter requirement, MOCAC replaces the expensive multi-gradient backpropagation entirely. It substitutes it with proximal policy optimization advantage estimates. This advantage metric can be computed through a cheap, single forward pass through the network during standard PPO training. Once the system has those advantage estimates, it can solve the dynamic weighting for the objectives offline using a highly efficient Frank-Wolf convex optimization algorithm. Theorem 1 guarantees precise multi-objective alignment while dragging the massive compute cost directly back down to the baseline requirements of standard RLHF. Moving from the theoretical architecture to applied practice, we can observe Moochok operating on a massive 7 billion parameter network like Llama 2. The researchers evaluated the model across competing behavior dimensions, balancing humor versus helpfulness and harmlessness versus helpfulness. Here, we are looking at the resulting Pareto front scatter plot for these experiments. The Moochok data points form a distinct, optimized outer edge curve, dominating the tightly clustered results of baselines like rewarded soups and Rick. The plot demonstrates a strict monotonic correlation. The rank order of the model's actual behavior perfectly reflects the numerical preference weights provided by the user. To quantify this success, the researchers measure hypervolume, a metric that calculates the total objective space dominated by a given solution. Mock registers a dramatically higher hypervolume than the competing methods, confirming both superior convergence to the Pareto front and a much wider diversity in generated behaviors. Baseline methods like Rick fall short here. They rely on prompt conditioning techniques at inference time, lacking any explicit mechanism to improve the policy itself. Because Mock integrates rigid multi-objective constraints directly into the policy gradient, it extracts maximum performance while maintaining absolute adherence to explicit user control vectors. Machine learning practitioners often view these results with specific skepticism, questioning if the model is truly learning the underlying alignment or simply memorizing the discrete preference vectors it saw during training. To test this, the trained LLM is fed a series of continuous, uniformly sampled preference inputs that were explicitly excluded from the training dataset. This plot shows the model's performance on those unseen preferences. Smooth, continuous interpolating curves form between the data points, showing seamless adaptation to entirely novel trade-off requests. This clean interpolation proves the LLM is not memorizing discrete points. It has successfully mapped the underlying multi-objective continuous manifold. Achieving this infinite granularity of inference time control required exactly one efficient fine-tuning run. This structural efficiency eliminates the need for developers to lock models into single predetermined preference averages. By combining rigid multi-dimensional reward constraints with a surrogate PPO advantage objective, Mock decouples large language models from the average, allowing for truly scalable, hyper-personalized AI.